Okay, we're going to get this one started because we are the last two people between you and happy hour, so we're going to try to make sure that we get this done. My name is Dale Parmentary. I'm Vice President of Operations from NEPA, which is an acronym for Northeast Pennsylvania Industrial Resource Center. Our mission is working strictly with manufacturers, and we're very happy to have you guys here. This will be the last presentation of a jam-packed day, so I hope that you guys have gotten a lot out of it. I know I have my staff here. This is a way for them to start to build a vocabulary when they're out calling on manufacturers. Today's speaker is Ed Graham from Protocam. He is the senior engineer at Protocam, and they produce 3D prototypes and provide additive manufacturing services, and they're based in the Allentown, PA area. He's a graduate of Penn State in plastics engineering, I believe. Yep. And what Ed is going to talk about today is the four main resin technologies that you heard a little bit about. He's going to go into a little bit more depth today about those. SLA, which is stereolithography, SLS, the Select Laser Sintering, and FDM, fused deposition modeling, and PolyJet technology, I believe, at the end. So without further ado, I'm going to bring Ed up.
Oh, good afternoon, everybody. The last one of the day. I want to start off by saying that I know Brian pretty well. I apparently know him too well because we have a lot of overlaps in our presentations this afternoon. So I just want to throw that out there and apologize for any redundancy here. But the good thing is that I know if you hear things multiple times, by the third time, it should be in there. So by the end of today, you guys should know everything there is to know about additive manufacturing. So I'll start off by just introducing the company. Like mentioned earlier, Protocam is an industrial 3D printing additive manufacturing facility. We're a service provider. We do not sell machines or equipment. We're located just an hour south of here in Allentown, Pennsylvania. This is our facility. We have about 15,000 square foot, and we will soon be expanding that to another 5,000 to a total of 20,000 square foot facility. We specialize in four main technologies: stereolithography, FDM, selective laser sintering, and PolyJet. So there's two ways that you go about making a part. There's subtractive versus additive. So since the beginning of time, cavemen have been working on the subtractive aspect here, whittling away something to create something. Also since the beginning of time, people have been making things in an additive nature, layer upon layer, building it up and creating a product from it. So we're going to start and focus specifically on, obviously, the additive side of this process. Just a brief history. As contrary to Brian said earlier, this is not a new technology, it's an old technology. Well, I'm 42 years old. I don't like to consider myself old, and this technology is a lot younger than me, so I'm going to say it's still a new technology. If I'm 42, I look at somebody 20, I'd say they're very young. So I'm going to consider this a young technology still. I'm not going to run through each of these bullet points here because it was covered earlier pretty well by Brian. The one thing I will say is that Protocam was started in 1994, so we have been in this business for 22 years. I can relate a lot to the guys at Imperial when they were talking about bins of bad parts. Well, over 22 years, we have truckloads of bad parts. But we've learned an awful lot, and I can definitely relate to what they were talking about. One of the things that we do at Protocam is when we fail at a build, we go at it until we get it right. We really pride ourselves in that. We don't give up on projects, and we really work hard to get them right. And our experience helps that. Additive has made it to the big league. It's got its own definition now in the ASTM. You can read this off. It's a process of joining materials to make objects from 3D models. layer upon layer as opposed to subtractive. Another name for it is 3D printing. The first thing necessary in order to do any 3D printing or additive manufacturing is the need for 3D CAD. And of the 3D CAD file, it's important to have an STL file. Now, I know it's getting late in the afternoon, and I'm really sorry for the food picture up there, that gorgeous piece of roast beef. But the analogy I have here is if we were to take this part, throw it onto this meat slicer, we would slice the file up into layers, and that's the process of additive manufacturing, building a part one layer at a time. There are a lot of different CAD programs out there right now that have the ability to create STL files. From Autodesk, they're becoming a big leader in this industry. Autodesk has really come out. When I started years and years ago, Autodesk, AutoCAD, they were very low-key. They weren't really in the game too much. They were more of an architectural, they weren't in the 3D world. But now with a lot of their generative CAD modeling programs, they're really becoming a leader. They're getting into the industry with the printers, the platforms for running them. So they become a big player in this industry. SolidWorks, obviously, Creo, former pro engineer. On a consumer level, if you don't have those capabilities for the high-end CAD programs, there are a lot of consumer-level programs out there that you can download. They're free, they're pretty interactive, and you can muddle something together and build something. If you have no CAD skills, CAD experience, no desire, you can go to one of the many community STL sites that are out there, Pinshape, Sketchfab, GrabCAD. Probably the leader is Thingiverse, and you can see they have great products like a 3-bag holder that you could download. I mean, who doesn't want one of those? A 3-bag bag holder. I mean, I go there all the time for stuff like this. This is really good stuff. So if you don't have those CAD skills, get on Thingiverse. Social media and crowdfunding has been a big part of the 3D printing boom. I mean, it's the one that really kind of skyrocketed it with the Kickstarter campaigns for the consumer level machines, the tweets, even as far as my mom, she's 70-something years old. I actually know her real age, but if I would say it, I guarantee a lightning bolt would probably come through here and hit me because she'd kill me. But she's in her 70s, and yeah, she watches The Big Bang Theory. And she actually called me and told me about the episode where they showed that 3D printing thing that I invented. I thought it was great. I mean, she's 70-something years old. Let her go. That's awesome, Mom. You keep watching. You should get on a tweet about that. She didn't know what I meant when I got into that. So the consumer-based 3D printing, I mean, again, this was what the hype curve, you know, you can almost see this is going right up. In 2007, you know, there was only 66 units sold. By 2014, there was 140,000 units sold on a consumer level. And people would say, oh, aren't you guys terrified of that? I mean, you guys, this is your business. Aren't you scared of these consumer levels coming out and taking over your world? And no, we actually welcomed it. It was like, well, let them do it. Let them bring it in. Start getting used to it. Start using it. See what the capabilities are. See what's achievable. And it really did. I mean, I think we've seen a growth in business when these came out because, number one, people did two things with it. They said, hey, this isn't for me. I don't want to be in this world. Or, hey, this is for me. And what I'm doing on this is great, but I really need the next level type of products. I need the next level. I need those higher materials. I need the things coming off of the 3D printers or the industrial level printers. So it was really a benefit for us. They come off with low cost, safe to use, easy to use. I don't know. Talk to a lot of people who run MakerBots or Form 1s, and you can ask them about the ease of use type of thing. But it really fueled the fire, I think, for us. And that's where we're going to get into, you know, the industrial side here and start diving into that. The first technology I want to talk about is stereolithography. You guys probably have heard that enough today to know exactly what it is and what it's all about. But there's several different manufacturers when we're talking about stereolithography systems. 3D Systems, Chuck Hull, the inventor, that's the biggest one by far. EnvisionTEC is another really big player in the arena. They have some nice systems. Theirs is not laser-based, but more DLP, and they actually do a Blu-ray type system as well. Prodways is a new company that's coming out. I think they're based in France, and they've been on the market not very long, and they're doing large frame DLP systems. Most DLP systems have been traditionally consumer level, and they said because it's not a scalable technology, it's very difficult to scale DLP. But Prodways has come up with a way to do it, and they say it's pretty good, because you're covering a lot of surface area really fast with DLP versus a laser tracing every point of geometry. So there's some real benefits to that. It's just whether or not it's a reality, I don't know. I haven't seen any parts off of it. Large frame systems, you're talking in the range of $650,000 for a unit. These are not inexpensive pieces of equipment. Like we heard from our friends at Imperial, auxiliary equipment, there's a lot more that goes into this than just this $650,000 for the SLA machine. You can look at the build envelope here. We're talking 25.5 by 30. Resin costs, again, $250 a kilogram. And then there's also maintenance costs that go along with these equipment. On a consumer level, stereolithography is still there. There's a system out here on one of the tables, the Form 1. That's a laser-based consumer level SLA. You have the Spark by Autodesk, and there's some other DLP-based systems out there as well. So the process itself, how does stereolithography work? We start with a vat of liquid photopolymer. We take our CAD file, slice it up on that nice meat slicer, draw the laser into the vat. Everywhere the laser hits the vat, it starts to build and solidify the resin. The elevator lowers as it goes, and this continues one layer at a time until the part is complete. There is a little video here, but I'm not sure that it's going to work. No, it didn't. So this is just a sample of a build platform off of a stereolithography machine. And if you notice, under each part, there's this little lattice structure that you see there, and that's the supports. That's that dark side of 3D printing that people aren't really aware of. They talk about just hitting print and out comes a model. Well, the supports are the dark side there, and I believe with your $125 paid thing for today, you get to see me again tomorrow, and I get to go over all of the post-processing. So this is a good deal. This is a good deal. This is better than like a Ginsu knife here. So maybe not better than a ShamWow, but definitely a Ginsu. Advantages of stereolithography. The biggest one by far is the dimensional accuracy and the smooth surface finish. They're the two characteristics. Every time you hear anybody talk about stereolithography, they are the characteristics that come out shining every time. The nice thing about it is that parts can be sanded, they can be painted, they can be dyed, electroplated, and if you had a chance to stop at our booth, there's lots of samples out there with stereolithography parts. Some of them may not look like stereolithography parts, so ask and we will show you all of the different parts, which ones are not, because we do a lot of painting and post-finishing work at Protocam, and a lot of the parts out there are in fact stereolithography. You like that title of this one, right? I came up with that all by myself. The clear advantage. So when you're talking about clear parts, stereolithography by far is the best technology. If your focus is on wanting to make a clear prototype, a clear part, stereolithography is the only choice. Other technologies offer clear. I think PolyJet has a clear resin. They do have a clear resin. Not a big fan of it. But this is actually a part that we prototyped. We've developed actually an in-house proprietary process where we can create bottles very fast and very clear. And And again, this goes back to that 20 years of experience. Everybody that looks at any bottle that is in our facility wants to know, how did you do that? Because it's a work in progress. Another area of use for stereolithography is in patterns. Protocam does a lot of RTV molding and urethane castings. Anybody that has ever had urethane castings done off of an RTV mold, 90% of those patterns were probably stereolithography. And again, it lends itself back to that great surface finish, great accuracy, and the ability to paint and sand the models. So you take the part, you prep it, then you build a mold around it. You take the mold out, take the SLA out, inject your urethane inside of there, and then you can create urethane castings. So that's and it's also used in patterns in other industries as well. Sand cast patterns, another big industry that uses stereolithography. Stereolithography has two different main build styles. That's one thing a lot of people also don't understand. The main build style associated with stereolithography is an ASIS build style, and that builds parts in a solid structure. One other way that we can build parts using stereolithography is in the quick cast. And the quick cast is basically taking a part and hollowing it and filling it with this beehive structure. Now, what that little bee is doing on there, pushing a lawnmower, I have no idea. I do have teenagers in the house, and I'm thinking they might have had something to do with that. But I'm not sure how that relates to anything, so forgive that. Let's see here. So more on the quick cast. I mean, when you start talking about quick cast, basically what happens, and we have a quick cast pattern on our table out there, and I encourage you guys to take a look at that. You know, it's a really nice way. We take the part, build it in this build style. It's a honeycomb structure. You start by building the part, then you send that to a foundry. A foundry will take that and dip it into ceramic. Just like this is for the investment cast process. They'll dip it into ceramic, coat it one layer at a time, build up this big shell on it, then they'll fire that shell, burn the SLA out of it, and then inject the metal inside of the cavity, and then you have a metal prototype. I was recently at AMUG, and I was involved in a presentation where they were talking specifically about quick cast, and they said that stereolithography is still by far the leader in investment casting technology. 80% of investment cast prototype parts are using stereolithography. There are some other technologies out there. You can do wax patterns, you can do voxel jets, other technologies, but by far stereolithography holds that industry. From an additive manufacturing standpoint, we saw this slide a little earlier today. But again, this is really a perfect, and that's why you will see this over and over again. It's a perfect example of using these technologies in an additive manufacturing standpoint. The Invisalign process. I mean, they're taking scans of your mouth, they're printing out patterns, then from there they're actually thermoforming a plastic over the SLA patterns. So each time they take a scan of your mouth, they have software that figures out the 7 steps of how your teeth need to be formed in order to get them to that right end result. So each pattern has to be built for each person, so it's mass customization and it's mass additive manufacturing. It's a really great application for the technology. You can actually see the layer lines on there. See that? So the next technology you're going to get into is selective laser sintering. Again, 3D Systems is a major manufacturer of this type of equipment. EOS is probably on top of them by now, I would say. I don't know, in the market. EOS is probably on top of 3D when it comes to polymer-based selective laser sintering. And Prodways, again, has entered that market as well. I think they had some people that left 3D and went to France and went over here and came back and went over here and then went over here and then came back to here and then wound up at Prodways. So you're probably getting the same machine, just out of France. Large frame machines here, you're talking $900,000. This is big capital. This is not a small investment by any means. They do have big build envelopes associated with them. Resin costs, you can see, are lower than stereolithography. And there still is this annual maintenance associated with the machines themselves, $45,000 a year just to maintain it. How does the process work? So again, you're starting with a bed of powder, nylon powder. And in that bed, you're basically, in essence, taking that bed and you're heating it. You're heating that bed almost to the point where that powder wants to kick, wants to melt, but it's just not there yet. So what happens is the laser comes down and shines in there, and then it kicks it over, and it melts it and starts to fuse those particles together. Once those particles get fused, that layer drops. You take another fresh amount of powder, roll it across the top, and then we start the process all over again. One good thing about this technology is the fact that there is no need for supports. The parts are self-supporting in the bed, so it has some really unique advantages there. This is a typical build tray. If you see most build trays of other technologies, including stereolithography, they're a single layer, a single array. With SLS, you can actually stack, stagger, pack everything into this box. So you can really, really fit a lot of parts into one build. Now, keep in mind that one build is going to take a really long time to build. One other thing that goes along with SLS, which I'll get more into tomorrow with the post-processing, is that every hour of build time, you have an hour of cool down time. So if I built this whole box in 10 hours, I have to let it sit in the corner over here for another 10 hours before I can touch it. Some advantages of SLS, again, these are highly durable parts. I mean, these are nylon material. They have high heat capabilities, no supports. You can build some really complex geometries, and there's a variety of materials. Again, the nylon 12, there's a glass-filled version. Nylon 11 is a more flexible version, so you can do things like, I've done some living hinges with it. I've done some really good, if you have a lot of parts with snap features, things like that, they're really going to take abuse. The 11 works really nice. There's a big push right now in the industry to develop a nylon 6, which is very attractive for the automotive industry. It's a material that they use on a daily basis. It just takes higher heats to process it. It's a little bit more challenging. But I think that BASF just partnered with Prodways, and they're going to be working together to bring PA6 available. Where is it used in additive manufacturing? Same scenario, an air duct for a Boeing plane. I mean, this is where they're using it. You can create really complicated shapes and design some really intricate things with this process because of its no supports and the freedom with the design, and as well as the balance between the good mechanical properties. Really, this lends itself well to a selective laser sintering. Just as a real quick analogy or a case study almost, you could say, if I were to take the example shown here and build this part, this duct, conventionally, this would make up approximately 16 pieces to make this part. You're going to have a top piece, a bottom piece, a baffle in the middle, a bracket that goes over it, the screws, the hardware, everything involved with that. And with this technology, I can reduce it down to one piece. So, aside from it being lighter weight, probably more efficient, and just a better part overall, look what it does to everything from a whole company standpoint in terms of inventory control. You don't have to have all these parts on control anymore. Supply chain management, look how it affects that. It affects every aspect of it. So that's why there's a big push to start taking a look at parts from all these industries and saying, hey, what other parts can we take here and reduce the part counts down, And like Brian mentioned earlier, we're going to reduce the part counts down. Yeah, that part is a little bit more expensive than that, but it's lighter weight, so that equates to fuel savings. And when you're talking to aerospace, fuel savings are everything. And if you can get parts weight down, reduce part count, inventory, supply chain, I mean, it's really a win-win. It really is. And selective laser sintering really lends itself to that. So I'm going to talk a little bit about FDM, fused deposition modeling. Again, I think the only major manufacturer of these type of systems is still Stratasys. I don't think there's any large frame. Well, you're coming out with like the big reps and Cosine, that's the one I was looking for, thanks. Cosine, but they're still not at the level of the large frame machines from Stratasys. Big frames here, $430,000 for a system. And that's with a build envelope of 36, 24, 36. Resin costs you can see here are still continuing to go down when you're comparing it to SLA and SLS. And the maintenance cost, again, I think this is a really user-friendly type of technology, and I think that's why it's really been adopted into a lot of different companies. As you know, people are saying, what should we start with? What should we get into? We want to get into this, but what technology should we bring in? And I think a lot of times they bring in FDM because it lends itself to a little bit more of ease of use. And I don't know if it's really true or not, because you still have failures and you still have issues to deal with, but ultimately there's no wet resins, there's no powders, it's a clean process. And I think that's why a lot of them get into it. What they really should be asking is, what is our application? What is our need? What are we trying to do here? And then going out and determine the right system for it. But I think it works a lot of times the opposite way right now. People are saying, hey, we want to get an additive, let's get a machine, what do you want to get? Well, let's get an FDM, that sounds good. And they don't really understand why or what it's about. So FDM, again, it started the consumer boom. I mean, it was the one that started it all. RepRap was really the first one. RepRap was developed over in the UK. A guy developed a printer that if you printed parts off of it, you could print your own. So if I print one for Brian, Brian can take his parts now and print one for you, and then you could take your parts and print one for him, and so on and so forth. And MakerBot saw this. MakerBot started to get involved in that. When they got involved in it, they were just a supplier of components. They were not even selling machines. They were selling you an extruder. They were selling you maybe the walls. They were selling you the control panel. They were selling you all this stuff, and you built it. And I guess more and more people said, hey, why don't you just put all that together for me? I'll buy it done. And so they started doing that, and then that's where it evolved. And the maker community got mad at them and said, we hate you, you're evil. But it was true. That's how it all started. Again, the process itself, how it works, you're taking two extruder nozzles. It's the hot glue gun analogy. Two extruder nozzles, heat the material up, you run it through, it squirts it out, lays it down layer by layer. There's a model material and there's a support material. Use one of each and build the part up one layer at a time. This is a sample build tray off of an FDM. Again, it's a single array. If you were really fancy, you could put parts on top of parts and get creative with it, but traditionally that's not how it is set up to do it. So it's a single tray. There's that bee again. I don't know where he came from, but he's back. So some advantages here. Durable parts. FDM makes strong parts. That's what it does. I mean, there's two technologies that are out there as what makes strong, durable parts. SLS is one, FDM is the other. They have durable parts, high heat. The nice thing about FDM is that you can do things like have sparse builds. You can build hollow structures. Maybe that's why the bee's there. It looks kind of like a beehive or something. Maybe that's what he's there. I don't know. But you can build hollow structures. Again, we have some parts out on our table you can take a look at where we stop the build prematurely so you can see what this does. And this makes lighter weight parts. It makes parts, again, possibly more efficient. The nice thing about this technology, when you're working with some of the, like the ABS materials, they have dissolvable supports. So you can take the part, again, you just hit print, throw it in there, you're done, got a part. Some of the higher engineering resins, not so much. The Ultems, polycarbonates, they're breakaway supports. So now you're building a part and you're actually physically breaking the supports off the parts. And that's real fun sometimes. Again, there's a variety of materials. So these are all materials that anybody who's in the injection molding world is familiar with. ABS, polycarbonates, Ultems. They come in spools, much like your weed whacker wire. That gets loaded into the machine, fed through, and extruded out. Where I've seen FDM really used in industry as a true additive manufactured part is definitely in the realm of jigs and fixtures. I mean, we talked about that a lot today. You've heard that a lot today. And jigs and fixtures is a big part of FDM business. The nice thing about it, again, is you have a lot of color choices. So, I mean, I've been in places where first shift has all yellow parts, second shift has all blue parts, third shift is all red parts. End of arm tooling, anybody who's involved in injection molding, again, end of arm tooling, FDM works great for that. FDM is a real big player in that industry, and that's where I see it grow the most. So the last technology we're going to cover is PolyJet. PolyJet was owned by Objet, who sold to Stratasys. And a large frame machine from them is, again, in that $400,000 range. Max build envelope on a machine like this, 16 by 20. Resin costs, it's going up on PolyJet. $350 a kilogram. And that's the most expensive resin of all the technologies at this point. Maintenance costs are a little bit lower. The PolyJet technology is a jetted process. So there are print heads along the bottom of the machine, 8 print heads that line up. Each print head has 96 valves. Each valve spits out dots per inch. It runs just like a 2D printer, and it spits out materials in dots per inch, followed by a light source. And the light source, every time a dot is dropped on the table, it's cured by the passing of the light source, one layer at a time. The table moves down, and it continues the process. An example build tray of PolyJet parts. Again, it's that single layer, single array. You could probably get fancy again with this and put some parts on top of each other if you wanted to. But it's really not the premise behind the technology. Some real advantages of PolyJet is the high print quality. I mean, PolyJet prints compared to stereolithography in terms of wall quality and accuracy. If you want really nice wall quality, you want presentation models, you want good surface finish, PolyJet is the answer, if that's what you're after. The other nice thing is it's the only system that has a real variety of materials. So it has the ability to blend materials. You can load, right now we have a Connex 3, we can load 3 different materials in at one time. And if you, again, stop off at our table, we can show you some examples where you can build multiple durometers across the same platform, across the same part, all at the same time. It's really cool stuff. They're coming out with new materials. You're blending not just hard and soft to make elastomers. They have a digital ABS material that, again, combines that strength and surface quality. PolyJet, if you've been seeing anything about injection molding cores and cavities, printing out cores and cavities, and they've been this green color, this is the PolyJet technology. People are using this to actually create their cores and cavities. They're printing up the cores and cavities, putting them into an injection mold press, and pushing parts out. Now, I mean, you have to take this with a grain of salt. There's all sorts of materials out there. I mean, you're not going to push an LCP into this, but you could certainly probably process some polypropylenes, some simple materials, nice big gates, nice big vents, nice long cycle times. So this is not to be done to compete with injection mold tooling. It's done to compete with the speed of getting a real injection molded part quickly. So the way to do that is to print your cores and cavities off, load them in the machine, and run some samples. I talked about the blend of quality and strength. And traditionally, there's always been this battle of, all right, well, I want a strong part, something really durable, really strong. Where do I go? Well, you're going to go either FDM or SLS. Well, I want a really nice part. I want nice quality. I want this. Where do I go? SLA. Well, to me, PolyJet with the digital ABS really blends those two together. I mean, you can get some parts. I mean, this guy's working out with a part. I mean, how much stronger does it get? He's really flexing that thing there. I think that was me. I don't know. But this process really does some good stuff. And you can see at our booth back there, we have some examples of this. And I challenge you to go back there, pick some of these parts up, flex them, clip them, see what they're all about. Because in my eyes, this is definitely the one technology that really combines the strength and the wall quality into one, by far than any other technology. Where this is used in additive manufacturing, seen this earlier, these are hearing aids. They have a medical grade material. They also have a medical grade that is skin tone. So again, they're taking molds from people's ears, they're scanning them, and they're creating custom earpieces. So this is a great application of mass customization and additive manufacturing. So again, when we look at all these different technologies, you have to come to what's the value proposition of 3D printing? Why do I want to use it? What's it all about? I mean, when it first started in the industry, everybody was using it to make a prototype. They just wanted to get something quick. But as we're evolving here, year after year, and we're continuing to advance the technology, we're continuing to advance the materials, we're really starting to change the dynamics of what people are using this for. People were using it primarily communication models, marketing models. People were using it for bid packages. Hey, I got a tool being made over in China. I want to print a part and send it to them so they know what it's going to look like when it comes out. Not that I come back 8 weeks later and it's not the right part. People were using it for bid packages, jigs and fixtures. Then people were saying, hey, if I can print this, I can use this. I can use this for functional testing too, can I? Why not? This SLS is really strong. So now they're using it for functional testing. Direct manufacturing. I mean, we've been seeing examples of this stuff all day. People are using it now as direct manufacturing. The value, it's how you perceive, value, and what you are hoping to get out of this is how you need to look at it. What your goal is, what you're trying to accomplish with the technology, and that's where it's heading. So I think in an effort to get us out there and have a few drinks, I'm going to end now, unless anybody has any questions.
Do you see advanced manufacturing technology being able to handle volume as a direct manufacturing tool? So right now, I'm going to envision a factory with 100 machines. So where is it going insofar as handling volume?
I mean, I actually do see that happening. I mean, I see facilities just like an injection molding facility that's lined up with rows of injection molding machines. I see additive manufacturing facilities lined up with additive manufacturing printers. And the big example of that, Brian pointed it out this morning, is HP. I mean, HP is coming out with a system that they're saying is going to be 10 times faster than anything on the market, and it's going to have superior print quality, and it's really going to get us into that realm to start to compete with injection molding. And you know, once we start to get past the fact that these parts don't look like injection molded parts, it's going to advance even further. You know, we have to stop getting in the shadow of injection mold part finishes and quality, and, you know, A1 finishes. Once people start to adopt the surface finish that's associated with this, it's going to go even further. So I definitely see that there's going to be facilities that will truly be just like an injection molding facility.
And do you want to mention 3D Systems robot that they downloaded at NEPA?
Yeah,
That's kind of in the same thing.
yeah.
We were just at AMUG, Brian and I, and 3D Systems had their SLA bot there. And basically what they were doing is they were taking and building up, kind of like the clip technology, they were building parts up instantly, and this robotic arm would take the part and transfer it to different cells. And at the end of the day, it worked its way all the way down, all through the cleaning solutions, all the way up, and then output on the tray at the end. So it was pretty neat to see. Yeah.
Life cycle on these machines for the investment. When you look at 10-year, 20-year, 5-year.
I mean, as long as you maintain them well, I mean, we've had machines for 20 years that will hold up. I mean, as long as you maintain them well and as long as you pay your service contract, they do well. They do well. I mean, they have failures, don't get me wrong. I mean, every process and every technology does. I mean, we've come into just disasters in the machines, but, you know, it's all part of, you know, taking care of the machines, maintaining it, and if you do that, as with anything, it'll last for a long time.
What's your typical ROI? Just put it on your floor. What do you start making money for it?
I don't really get into the financial side of that, but I'm going to say 3 years.
3 years?
Yeah. Way in the back.
So Ed, I've been walking back and forth, so I apologize if you covered this, but given some of the types of suggestions you're making, is there sort of patent obsolescence risk as a result of some of these technologies? I'm a manufacturer, I've got a patent, now somebody else is going to go make this part that I make traditionally with my patent through the additive process. Does that put my patent at risk?
I mean, I don't know if this really, I mean, anybody can still go out and develop a product, whether using this or not. I mean, IPO and patents, that's a tough one for me because I'd rather see people invest their money in developing the prototypes than putting it into patents. Because at the end of the day, when somebody wants to take your product, they can.
So my patent's still good is what you're saying?
Yeah, yeah.
In addition to the cost of the machine, maintenance, and consumables, what are your other expenses?
Overhead, employees, and auxiliary equipment.
The infrastructure. Right. Want to go into a little bit?
I'm going to say that for tomorrow morning because we have a post-processing presentation, and that gets into that other side of it.
Well, I'm also thinking about rebate electricity, HVAC systems.
Yeah. I mean, it's a big part of our facility.
How strict is the environment control around a machine like that?
No, I mean, we just exhaust them to the, you know, there's really not a whole lot of restrictions on that side of it.
You don't need to maintain a temperature or anything. The way they operate like a regular machine.
No, we like to run them in a humidity and temperature controlled environment for sure.
Better product or better machine? Both. Yeah.
All right, before everybody leaves, I think we give another